All right, here are the solutions to Gravitation 2. This is going to have a lot more calculations on it than the last one did. What I really need you to do is try them first and then look at the solutions. It will not help you on your quizzes or on your tests. It will not help you to learn this material if you just watch me do the solutions. It will only help you if you are checking work that you've already done and looking for what went wrong. So, here we go. Describe the relationship that determines the force of gravity between two objects. What factors does the force of gravity depend on, and how does changing them change the force of gravity? All right, well, the force of gravity is G, universal gravitational constant, times the mass of one object, times the mass of another object, divided by the distance between the centers of those two objects squared. Okay, so it depends on all this stuff. It depends on the mass, and it depends on the radius. If one mass is doubled, the force is doubled. Give me some room. Those things on top are what we call directly proportional. Right? If I triple one of the masses, I'm going to triple the force. If I double one of the masses, I'm going to double the force. That's just how the math up there works. However, radius is a little crazy. If the radius is doubled, one, because it's in the denominator, it's going to make the force smaller. And two, because it's squared, it's not just going to be halved, it's going to be quartered. So if the radius is doubled, we're going to take that force and we're going to cut it into fourths. Right? If I triple the radius, I'm going to have 1/9 of the force that I had before. So, because it's on the denominator, that's indirectly proportional, and it's squared. That does all kinds of, sorry, it's not indirectly proportional, it's inversely proportional. And because it's squared, we're going to have to square that factor. And these next ones are going to be sort of practice doing that. So two objects, each of mass m, are placed a distance d apart, and the force of gravity between them is a magnitude Fg. What happens when? That's what's going on with this. So our original force, Fg, is G times m over d squared. So if the mass of one object is doubled, what we've got is the force for part A is going to be G times 2m times m over d squared. This is how I want us to go through this. Instead of writing m down, we're going to write down 2m because it's doubled. And so I have 2, I just want to pull that all the way out, times gmm over d squared. And if I compare this, this statement is 2 times this statement. So my force, if I double just one of the masses, is twice the original force that we had, which agrees with what we set up here. If I double one mass, the force is doubled. Here's the math that goes behind it. What happens if the mass of both objects is doubled? So in part B, we have G. We're going to double one of them. That doubles the force. We're going to double the other one. That quadruples the force over d squared. So if we move those 2's together, what I've got is 4 times gmm over d squared. That's 4 times this, so it's 4 times Fg. If the distance between them is doubled, for C, and this is what we talked about in question 1 a little bit, I've got G times m over 2d squared. So I'm going to have to take that square and apply it to both things. So I've got gmm over 2 squared, which is 4 times d squared. So that's 1/4 gmm over d squared. So that's 1/4 of the original force that we had before. Mathematically, that's how it works out. So if the distance between them is doubled and the mass of both objects is doubled, so for D, we have all sorts of things going on. We have G times 2m times 2m over 2d squared. So from the top, we get 4gmm over, and then on the bottom, we've got 4d squared, because we're squaring both of those things. Well, the 4's cancel out, and I'm left with just gmm over d squared, which is the exact same thing as fg. And this is where that comes in handy. This is a different application of that same problem. You're going to go to a planet that has twice the mass of Earth with the same radius. How would your weight compare? All right, for this, you know that on the Earth, the force on you is going to be G times the mass of the Earth times your mass divided by the radius of the Earth squared. Well, if we go to this new planet, force on the planet, G, that's the universal gravitational constant, it doesn't change. But we have a planet that has twice the mass of the Earth. Your mass is the same. And then that planet also has the same radius as the Earth squared. So all I've done is double one of the masses just like we did before. I've got 2g mass of the Earth, your mass over the radius of the Earth squared. So that's twice the force of gravity that you have on the Earth, which means you have twice the weight that you did before. Your mass didn't change, but because you're on a different planet with a different gravitational force, your weight has changed. Same deal. We're gonna get on a ladder, and so we're one radius away from the surface of the Earth, which means you are 2 radiuses from the center of the Earth. So if this is the radius of the Earth, you are on a ladder that takes you here, another radius of the Earth away. So your radius is now twice the radius of the Earth. On Earth, just like we had before, the force of gravity on the Earth is G times the mass of the Earth times your mass over the radius of the Earth squared. That's what's happening when you're standing on the surface. But now, your force on this super magical ladder, well, the mass of the Earth is the same, your mass is the same, but we have twice the radius of the Earth now. When you do that, the force of gravity doesn't go away. The force of gravity is now G times the mass of the Earth times your mass over 4re squared. You have 1/4 of your weight now. Your mass is still the same, but you are far enough away that you have 1/4 of your weight. In videos of the moon landing, the astronauts appear to bounce when they walk. They don't feel like they have as much gravity on the moon as they do on the Earth. Why do they feel less gravity on the moon? The moon has less mass than the Earth. So it can't pull as hard as the Earth. Sorry about that. It cannot pull as hard as the Earth. So what that means is that the astronauts have less weight on the moon than they do on the Earth because there's less mass to the moon. All right, number 6. 2 students are standing 1 meter apart. Each student has a mass of 100 kilograms. Calculate the gravitational force between these students. And then why don't they notice this gravitational force? To calculate any gravitational force, we're going to do G times m over the distance separating those masses squared. G is a number. That number is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, times one of the masses, 100 kilograms, times the other mass, 100 kilograms, divided by the radius, 1 meter squared. Now, when using this formula, looking at all the units, meter squared goes away. Kilogram and a kilogram and a kilogram and a kilogram all go away. So when you do all of that, the units work out to be just newtons. That's all we're left with. Now, we got to do the rest of it in our calculator. So the important thing is that when you do times 10 to the negative 11th, in your graphing calculator, you do the second, and then you do the comma button. So second comma. There's a comma button, there's the second button, because you want it to show the little e symbol. You don't really want to do the times 10 to the. You want to show the e symbol because it tells your calculator to treat that like a number. So when you put that all in your calculator, you end up with 6.67 times 10 to the negative 7th newtons. Why don't you notice this force? That is really, really small. Right? That's a super, super, super small force. We don't have anything that can even measure things that small. In order to get any kind of gravitational force because of this universal gravitation number, we need a whole lot of mass. So we're going to do that here. The sun has a mass of 1.99 times 10 to the 30th kilograms, and the Earth has a mass of 5.98 times 10 to the 24th kilograms, and that's how far apart they are. I want to calculate the force of gravity acting on the Earth by the sun. So the force of gravity acting on the Earth by the sun is G times the mass of the Earth times the mass of the sun divided by the distance separating them squared. So we got to put all those numbers in. G is 6.67 times 10 to the negative 11th. The mass of the sun is 1.99 times 10 to the 30th. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And they are separated by a distance of 1.496 times 10 to the 11th meters. And then that whole thing has to be squared. So in order to find that force, you need to put it all into the calculator. And so what I have for you is a little calculator that we can do that with together. I don't know if we can do a little indicator here. So you just have to watch this little dot, I guess. So 6.67, and then we're going to do second comma, that gives a little e, negative 11 times 1.99 second comma, so e, 30 times 5.98 second comma, the e button again, 24, that's the Earth, divided by 1.496 second comma 11, and since it's treating it like one number, I can do squared. So we hit enter, and we see that that force is 3.5 times 10 to the 22nd newtons. That's a really, really big force. The sun has a lot of mass, the Earth has a lot of mass. And even though they're really, really far away, that much mass gives you a lot of force. Now, it turns out that because of Newton's third law, the force Earth exerts on the sun is equal to the force the sun exerts on the Earth. It's going to be the same because of Newton's third law. All right, so number 8, we've got the force. What we want to do is calculate the distance. So I know the force of gravity is g times mass 1 times mass 2 over the distance separating them squared. The thing that I don't know is that distance. Now I don't want to do math with all those big numbers, so I'm going to do math with just letters. If I want to solve for r, I need r on top and by itself. So I'll multiply both sides by r squared, divide both sides by the force of gravity, and so what I get is that the radius squared is equal to g times mass 1 times mass 2 over the force of gravity. So if I want that radius, it's going to be the square root of 6.67 times 10 to the negative 11th times mass 1, 1 times 10 to the 6th, times mass 2, 4 times 10 to the 6th, divided by that whole force, 1.67 times 10 to the negative 3 newtons. And again, I want to show you how to do that on the calculator, so we're going to pull that calculator up. So second square root on the top, we're going to have to do that, 6.67 second e negative 11 times 1 times 10, so second comma e to the 6th, times 4 second e 6th, divided by, I don't want to put the parentheses there, I just want to divide by 1.67 second e little negative sign 3. That's exactly what we have there. It's easier to do it all at once. Please do it this way in your calculator. And when we come out to that, we get 399.7 meters away. All right, next one. A very large asteroid is this far from the Earth and it's attracted to the Earth with that force. Determine the mass of the very large asteroid. So here, that force is g, mass of the Earth, mass of the asteroid, divided by the radius squared. What we want now is the mass of the asteroid. So we have to move everything else over. So we're going to multiply both sides by r squared. That makes that go away. Then we have to divide both sides by g. That makes that go away. And then divide both sides by the mass of the Earth. That makes that go away. So what we've got is that the mass of the asteroid is equal to the force times the radius squared divided by g times the mass of the Earth. So we'll put all that in. So the force, I'll do a different color, 3.19 times 10 to the 25th times the radius squared, so 1 times 10 to the 5th squared divided by 6.67 times 10 to the negative 11th divided by the mass of the Earth, 5.98 times 10 to the 24th. Again, to put this in our calculator, if you feel confident with that, you don't have to, you can forward past a little bit. We're going to have top part, 3.19 second E25 times 1 second E5 thing squared. And again, because we're using the E button, it's going to treat that whole thing like one number. that's the top, divided by the bottom, 6.67, second E, negative 11. And then it's on the bottom still. We're still leaving it in the parentheses times 5.98 second E 24. We've got everything entered in one line. Makes it easier to do. Comes out to be 7.997 times 10 to the 20th, or 8 times 10 to the 20th kilograms, which is a big asteroid. Planet has this mass, this radius. Calculate the weight of a 50 kilogram object on this planet. And for this one, I'm not going to show the calculator again, but if I want the weight, that's the force of gravity. So it's G mass over R squared. 6.67 times 10 to the negative 11th times 8 times 10 to the 25th mass of the planet times 50 mass of the object divided by 6 times 10 to the 6th meters squared. When you put that into your calculator, you get 7,411 newtons. Last one, while landing on a barren, deserted planet, a group of astronauts find the acceleration to be 20. They already know the radius is that. Calculate the mass of the planet. So here's how this works for acceleration due to gravity. I know that the force of gravity is equal to G times the mass of the planet times the mass of an object divided by the radius of the planet squared. But I also know that the force of gravity is equal to the mass of an object times the acceleration due to gravity. Well, I can set those two things equal to each other. Mass of the object times the acceleration due to gravity is equal to G times the mass of the planet times the mass of the object divided by the radius squared. The mass of the object goes away, and I'm left with G, the acceleration due to gravity, is equal to G, the universal gravitation constant, times the mass of the planet divided by the radius of the planet squared. Now, if the only thing we don't know here is the mass of the planet, we'll multiply both sides by the radius squared, because we want to get the mass of the planet alone, divide by G, capital G, because we want the mass of the planet alone. And what we've got is that the mass of the planet is equal to R squared times the acceleration due to gravity, little g, divided by capital G. And so the mass of this planet is going to be the radius of the planet, 5 times 10 to the 5th meters, times the acceleration due to gravity on the planet, 20 meters per second squared, divided by 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. So we'll put that into the calculator, and I guess I'll show this one. So for this one, it's going to be 5 second E, that's what we do for times 10 to the 5th, times 20, divided by, close parentheses, well, there's just one number. Still do it. 6.67 times 10, second comma, to the negative 11th. Oh, and you know what we forgot to do? We forgot to square the 5.5 times 5 times 10 to the 5th. So we'll go second insert. Oop, did it wrong. Delete that. We want to make sure there's a squared there. And so the mass of that planet comes out to be 7.5 times 10 to the 22nd kilograms. And again, that has to be squared up there because the radius has to be squared. All right.